Good afternoon, Boby.
Good afternoon. Good afternoon.
So we've switched seats today.
Yes.
That means, are we going to talk about something new or?
Must be. That's what I've expected.
Yeah. So today we've been doing resistive type
Correct.
measurements, sensors.
Yeah.
For the past few weeks, and today we're going to talk about electromagnetic sensors.
Oh.
Okay. So basically, sensors that use the electromagnetic
Principle
phenomena
for the sensing.
for sensing purposes, right? So compared to resistive, now we've switched to electromagnetic. So when you talk about electromagnetic sensors, now electromagnetic is what? You have a bit of electric gas, magnetic field,
Yeah.
a combination.
Yeah.
There, right?
I can feel it is not so. I mean, it's going to be tough to follow. Hope I will not sleep.
Well, hope not. So in this course, we're going to cover the principles of magnetic field sensors, okay? And we're going to talk about four different types of electromagnetic sensors, magnetic sensors specifically. The first one's called surge coil, right? And flux gate sensors, right? Then they fall under what we call magnetometers. Then we're going to talk about something called magnetoresistive sensors, okay? And finally, we'll talk about Hall effect sensors. Now, we're going to talk in detail about each and every one of these sensors as I go along.
So far, I've heard only surge and coil separately. This is surge coil.
This is surge coil.
Similarly, flux, we know, gate, we know. So these are all seems to be really new.
Yes, but widely used in industry. And then we're going to talk about utilizing electric fields for measurements. Okay, so in the first section, we'll talk about magnetic fields. And in this next section, we'll talk about electric fields. What kind of things can we measure using electric fields? And here, we're going to focus on what we call capacitive or interdigital type sensors.
Mm-hmm.
And here, we'll talk again about the principles of electric field measurement. Bit of a sensor design and performance evaluation, and briefly we'll talk about fabrication and different applications. These sensors.
So the first one is actually, it's about kind of measuring the magnetic field.
Yes.
Am I correct?
Yes, correct.
Okay.
First one's about specifically measuring magnetic fields, and again, right? So the applications depend on if magnetic fields can be used to obtain some information about an object of interest, for example.
Got it.
Again, when it comes to electric field sensors, right, you might wonder why can't we use magnetic field sensors for those specific applications, but you'll see, again, it depends on the properties of the object that we are trying to measure. Or certain.
So depending on the application, we will come to know which one is best suited for that.
Yes. Now, even within these two different sensors, magnetic field and electric field, you see different principles. You kind of tweak the principles and then use them for different applications.
Is there Hall effect also?
Yes, we also have a Hall effect sensing. Okay. So that's basically, that's what we'll cover in electromagnetic sensors. And again, later on, if we have time, we'll probably talk a little bit later on in the course. We can talk about how you can maybe, let's say, design and fabricate, MEMS type distance. But again, we'll see how it goes. Now, what are electromagnetic fields?
The sunlight is also an electromagnetic field?
Well, light is electromagnetic kind of. Sunlight, I'm not sure. That's a good question. But this is a question you asked me in the previous slide. So if you're thinking about electromagnetic fields, you're thinking about either exploiting electric magnetic fields or a combination of both to basically obtain information about something, right? Or you want to sense something,
Yeah.
right? You want to see the response of that certain
Correct.
object of interest when you, let's say, have electromagnetic. It's either magnetic, electric, or electromagnetic. Now, Bobby, let me ask you. So you said, you talked about the sun, right? Naturally occurring, obviously. So when we talk about electromagnetic fields, are they ambient? I mean, do we need to produce them? Are they, are they naturally occurring, for example? Or?
I think it depends. See, for example, Earth, we know it has got a magnetic. So if there are situations where we can make use of that for sensing, yes. But sometimes it may be interfering with what we wanted to sense.
Correct. So you're right. So Earth has a magnetic field, right? Which we call the geomagnetic field.
Yeah.
So in fact, we are surrounded by huge magnetic.
I think it's about 50 to 60 microtesla.
Yes. And so so this is what we call the magnetosphere.
Yeah.
Right. Yeah. And did you know that if there was no magnetosphere, we will not be here?
Yeah, we'll be finished by other things coming from.
Yes. Because there's a constant bombardment of charged particles from the sun, and you mentioned the sun.
Yeah.
Sun provides us sunlight, but also bombards us with a lot of things.
So anywhere from the universe, things may come.
Right. So the Earth's magnetic field is a very important, I think. Now, as you said, it's about 25 to about 65, 70 microtesla.
Yeah.
But it's constantly changing.
It is changing. Also, I think if there are, let's say, some areas where certain ores are present, then there will be slight deviation in the magnetic field.
Absolutely.
In fact, people use that as a way to search and find out.
Interesting you said
where
that.
Such, large amount of ores containing magnetic material.
Exactly. No, you make a very good point. So if you look at the Earth, then, at the core, we have some kind of a core.
Yeah.
It's core.
Yeah.
And in fact, you can think of the Earth, like Earth has a giant bar magnet inside. Okay. So let's say something like this.
Yeah, somewhat like that.
Like this. I mean, my picture is not the greatest, but
yeah, it's clear.
Okay, it doesn't cross like this.
Yeah.
Let's say you go out here. Maybe put out here. So anyway, so field goes from north to south, obviously.
Yeah.
Okay. Something like this. But my question is, Earth has a magnetic field. And if you look at the Earth's magnetic field, if you look at the magnet inside, the bar magnet, the virtual bar magnet inside, it's something like this. But then we call this
North Pole and South Pole?
North Pole and the South Pole. If the Earth's north is here and south is there, why do we call this the North Pole and the South Pole? Now you might find the answer, right?
Maybe if I'm using a magnet to find out which direction
you're getting there.
Okay.
You're getting there. Okay. So here we ask the next question, right? Let's say we're talking about the Earth's magnet.
Yeah.
How do we characterize this field? Is there a passive way to do it? Is there an active way? What do you think?
I can use a compass.
Okay. We're getting there.
Yeah.
Can use a compass, right? Just like has a tiny little magnet inside, something like this. And it's been used for navigation for long time.
Yes.
Right? For many years. Now, a general compass, obviously, will look like this.
Yeah.
North, south, east, and west. Okay. Now, if you use a compass, right? If you use a compass now, where would this north pole? Where would this north?
Yeah. North will target towards south of the Earth.
Right.
So that's the reason.
That's it.
Okay. Nice.
So, I mean, compasses have been used for a long time. And when you have a compass, it attracts to the south this virtual magnet inside the core of the Earth, right? Which is why we call the North Pole and the South Pole. Now, those are ambient fields. Do you think we can also use some kind of active form of measurement using electromagnetic waves? Is that something that you use?
Yeah, I can form electromagnets maybe using a couple of turns, passing some current through that.
That will create
a magnetic field.
Okay.
Maybe we can put a ferromagnetic material also inside so that it may become stronger.
Mm-hmm. So we can also create our own
magnetic field.
Right. But if you talk about active kind of measurement, right? Another example is probably radar.
Yeah.
Where you have, like some kind of a satellite. Again, my picture won't be great. And let's say, you have an airplane or something.
Yeah.
And, this sends out electromagnetic waves.
Yeah, your aeroplane is actually nice.
Thank you. And the radar
there's a reflection.
There's a reflection back. And based on that, for example, one of the information you can get is how far this airplane is.
Yes.
Okay, so again, this is more of an active measurement where
Correct.
we are sending out something, an electromagnetic wave, and using that to detect an object. Okay, so it can be ambient, can be active. As you said, we can also produce our own electromagnetic fields. As you said, have few turns, send the current, and create an electromagnetic field. So both.
Yes.
Okay, so then what kind of modules are involved in electromagnetic monuments? Now, as you said, one of the things that you talked about is coil.
Yeah.
That's one way.
Yeah.
Probably the simplest way. Right?
We can also use permanent magnets.
You can also use permanent magnets. Correct. Okay, so, but if you're talking about electromagnetics, now, Boby, I'm sure you've seen these equations, maybe in your undergraduate studies.
Yeah, I think I have studied this.
I also did it some time back. But if you're talking about electromagnetic phenomena, right, there's no escaping what these equations.
So these are governed using these equations.
Or
we can use these equations to understand that and analyze better.
Yes. So all classical electromagnetic phenomena is generally explained by these equations, and these are called, you probably heard of this great scientist,
Maxwell.
Yes. These are called Maxwell's equations. So here, so Maxwell's equations, they come in both integral and differential form. Now here, I've shown the differential form of Maxwell's equations. So when we talk about Maxwell's equations, electromagnetic fields, and let's say the response of certain materials to these electromagnetic fields, we assume that we have linear dielectric and magnetic media, right? So that means in that material, if it has certain magnetic or electric properties, we assume that these properties are same in that material, right? I mean,
homogeneous,
isotropic, I guess is another word that you can use. But so when we are explaining this in the next few slides, we assume that this media is homogeneous. Okay. Now there are 4 laws here. Okay, 4 main laws. We have Gauss's law for static electric fields. We have Gauss's law for static magnetic fields. We have Faraday's law, which basically says that a change of the magnetic field will produce a change in the electric field.
Yes.
Okay. And then we have Ampere's law, which is the other way around. A change in the electric field will produce a changing magnetic field.
Yep.
Now, if you look at, so let's say 1, 2, 3, 4. If you look at equations 3 and 4,
yeah,
right? What does that tell you?
3 and 4?
Yes. So it basically forms the basis for electromagnetic waves, right? So that's why they can propagate on their own. But each changing magnetic field creates an electric field. that creates another magnetic field, and that creates another, and it just, so for example, light, right? We talk about photonics or light. Those waves travel by these changing electrical and magnetic fields, but we will not study light in this actual post section. Now, each of these equations describes...
Yeah, you have a lot of symbols and parameters. What are this? E, electric field?
Yes, you have an upside down triangle as well.
Yeah, what is that?
So each of these equations,
then
right?
There is a dot.
There's a dot. There's a
cross.
So each of these equations, right? They describe basically one phenomenon. Respectively. So we will look at each one a bit closely.
Okay.
So that the students can really understand what each equation means. Not necessarily from a derivative point of view. So I don't think we need to, they need to know how to derive this equation. But if you look at these equations, you need to understand what they mean. And also
physically what it means.
Physically what it means. And also I think it's very important when you're designing sensors, right? To I think these 4 equations, any sensor any electromagnetic sensor that you might design, will have to obey these equations.
Yeah.
Right. So I think it's worth to have a look at these equations.
So also sometimes for the sensor design, you may use certain tools.
Yes.
Some finite element tools, etc. So they actually use this equation to solve and give you the answer.
That's a great point. Yeah. That's a great point. Yes. So when you're designing sensors, obviously you do, some experiments, but also to understand certain aspects of that problem, you might use something like a finite element method. And in that case, yes, you need to understand its equations because you need to set certain conditions when you're modeling such sensors. So, great point, Boby.